Today, we're going to be doing some rational expressions review. So basically what I did today was I handed out a worksheet for you guys to work on. This video is where I go over those answers. So for the preamble here, of course, the review worksheet was handed out. Hopefully you've already done all this at this point. This is just because I'm gone today. But I'll go through each one right now. What I really want to stress, though, is I want you to make sure you make any corrections on your own work as I go through each question. So make sure you're filling in exactly what the actual answers are, as well as what the process is. These questions on this worksheet today are very, very, very much like what you can expect on your chapter test for this unit as well. Let's get going. So first question and the second question actually are both like rational word problems. I wanted to start with these because they often take a little bit more time. Remember, the key behind these kinds of questions is to make what I call a distance, speed, time chart. Even if it doesn't feel like it makes sense, identifying what you think could be a distance, a speed, and a time, it's really useful, right? So here's how we go about doing this in this one. First of all, draw my chart just like this. We do distance, speed, and then time. Up along this side here, I just always list like my two different situations. Well, we got Thelma and Louise. You could call it car and bike. To be honest, I think I'll just call it that just so it's a little more consistent. Car and bike, separate those. And then I always do a third column as well. You don't always use this column, but I like putting it in anyway. You never know if you're going to use it or not. I just call it the total column. So if we think in terms of our distance, we can see that both the car and the bike need to travel 15 kilometers. So for the distance, 15 kilometers is probably what we can put in there. Now, total, you might be tempted to go 15 plus 15 to equal 30. But in reality, both of these, like both the car and the bike, are both going 15 kilometers each. It's not stacking on to one another. They're doing the same trip, just, you know, in their own ways, right? So I don't think I'll put anything in the total column for that one. As for speeds, notice the question is asking for us to find their speeds. Whatever the question is asking us to find, usually that's going to be our x. Not always, of course, but like 9 times out of 10, that's usually what we're looking for here. So one thing I can get out of this, because it's hard to say, do I say car is x or bike is x? One thing that it says in the question is that the car travels 3 times faster than the bike. Because the car is going faster, I think I'll say the slower thing here. So the bike will be my x, and therefore my car will be 3 times x, or just 3x. Now, in terms of a time, the only thing that we know is it took Louise, so therefore the bike, half an hour longer, 0.5 hours longer to get there. But it doesn't tell us like exactly how long each of them went, right? So what we would do is, remember, distance is equal to speed times time. That's an essential formula that you're going to have to know for putting these together. If you were to rearrange this, though, you'd see that distance divided by speed equals time. It's that relationship that we're going to use to fill in that last row there, the time row. So time is just distance divided by speed. So for the car, we can just say it's 15 divided by 3x. And for the bike, we can say it's just 15 divided by x. Now, here's what's kind of funny. We know that it took Louise half an hour longer to get there. So if we said that Louise's time was equal to Thelma's time, that wouldn't quite be true. We'd have to actually add a half an hour to Thelma's time to equal Louise's time, because Louise's time is half an hour longer. So as weird as it is, the half an hour needs to go on Thelma's side, because I think of it this way. Thelma's time, so in other words, the car time, plus another half an hour is going to equal the bike time. So let's write that out. 15 over 3x plus 0.5 equals our bike time, 15 over x. And I'll say it once more. That's our car time, which is going to be less. It's going to be a lesser amount of time, plus half an hour equals the bike time, which is a more amount of time. That's why I had to put the plus half an hour on the side where the car was. Now, if you notice, this just becomes a rational equation, right? So it's an equation involving a bunch of fractions that have x's in them. In order to solve this, hopefully you remember, you just need to make sure they all have the same denominator. A common denominator I can get with all 3 of these would be 3x. I won't have to do anything to this first one, but if I multiply this middle one by 3x over 3x, that gets a 3x down on the bottom. And if I multiply this one on the far right by 3 on the top and the bottom, that gives me 3x on the bottom of these fractions. Now, here's the trick. I'm not going to write this down a second time, but here's the trick. Once all of the denominators in a rational equation are all the same, you can just ignore them. I want to stress that you can only ignore the denominators when it's a rational equation, when there's an equal sign in there. And that's what we have in this case, right? So long story short, we now have 15 plus 0.5 times 3x is 1.5x equals 15 times 3, which is 45. we want to get x all by itself now. So let's minus 15 from both sides. This gives me 1.5x equals 30. And then just divide by 1.5. Give me a second here. 30 divided by 1.5. That gives me x is equal to 20. Now, if you notice the units on this, we used hours for this piece. That kind of tells us that this speed, this x right here, would be kilometers per hour. So x is 20 kilometers per hour. That right there is Louisa's speed. It's the bike speed, right? So we found Louisa's speed. We know that the car travels 3 times faster than the bike. So just take this number, this x, and times it by 3 to get the car speed, right? So that'll be 60 kilometers per hour. And I'll box that number and I'll say that is Thelma. You could also call it, of course, bike and car, whatever floats your boat here. It doesn't really matter. Now, I know it says round to the nearest tenth if needed. Haha, we didn't actually need to. Anyway, moving on, next question. So Bob can shovel the snow from a driveway in 40 minutes. Doug can shovel the snow from the same driveway in 30 minutes. We want to find how long it would take to clear the snow if they work together, round to the nearest tenth of a minute if needed. These ones are a lot trickier. We did one like this when we were first learning this about painting a fence or something. It's a very similar idea. Once again, though, just set up your distance, speed, time chart. But something funny is going to kind of happen with this one. Distance, speed, time. We have Bob. We have Doug. And then just for fun, we do a total column. Don't know if we'll use it, but we always do it just in case. Now, in terms of a distance here, this is where things are kind of funny. Bob's distance, at least with what we're analyzing here at first, is going to be one driveway. Same with Doug. It's going to be one driveway. Now, this is before they work together or anything. We want to just kind of set the ground rules here. So Bob, one driveway, and Doug, one driveway. In terms of a speed, that we don't know. It mentions nothing about that at all. But it does tell us a time. It says Bob can shovel the driveway in 40 minutes. So he can get this job done in 40 minutes, whereas Doug can get it done in 30 minutes. Now, in total, of course, I think the total column actually has nothing to do with this one. So there's 2 questions in a row where we didn't actually have to use it. That's fine. But notice how our speed row is empty there. Well, just remember that distance is equal to speed times time. If you're to get speed by itself, that would be speed equals distance divided by time. So we'll just take our distance and divide by our time to get our speed. So Bob's speed is 1/40, and Doug's speed is 1/30. And remember, 1/30 is actually a bigger number than 1/40. So in other words, his speed is a little faster. Now, here's what's funny here. We want to find how long it takes for them if they're working together. Now, what's funny about this is if you look at the chart we made, everything in there is clear. We don't have an X or anything. But this chart was made assuming that they're actually doing an entire driveway each. We know in reality, if they're working together, they're not going to individually shovel a full driveway. One of them is going to shovel part of the driveway and the other is going to shovel another part of the driveway. As a matter of fact, I can say since Doug goes faster, Doug's going to end up shoveling more of the driveway than Bob would. However, what we need to understand is Bob's distance plus Doug's distance, so the amount of the driveway that Bob does plus the amount of the driveway that Doug does is going to equal one full driveway. Distance is equal to speed times time. Now, both Bob and Doug are going to be working for the same amount of time, and that's what we're looking for. We're trying to find how long it would take to clear the snow. Since both Bob and Doug are going to have the same time, let's call time our x. Now, distance is speed times time. So you could say Bob's distance is going to be his speed, which is 1/40, times the time, which is x. That would give us x out of 40. So Bob's speed times by his time, which is x, would give us his distance. X out of 40 is how much of the driveway that Bob does, plus Doug's distance. Well, that would be his speed times his time. Well, his speed is 1/30, and his time, once again, is x. So we can just say that's x over 30. Bob's distance plus Doug's distance is going to equal one driveway. In order to solve this rational equation, we just need to get common denominators here. I'm going to be pretty crafty here. Between 40 and 30, I think a good common denominator would be 120. To get 120 here, I just need to multiply this one by 3 on the top and the bottom. And this one, I just need to multiply by 4 on the top and the bottom. However, this 1 over here, it's technically 1/1. It also needs to have a denominator of 120. So I'll multiply it by 120 on the top and the bottom. What that's going to do is it's going to give each of these rational expressions a denominator of 120. So I can just ignore them all together because once again, there's an equal sign in here. This is going to give me 3x plus 4x equals 120. And then we're almost done on this one. 3x plus 4x, that would be 7x. They have like terms after all, so I can just add them together. 7x equals 120. To get x all by itself, we just need to divide by 7 on both sides. So I got 120 divided by 7, rounded to the nearest tenth, I'm getting 17.1 minutes. So if they're working together, it would only take them 17.1 minutes. So pretty useful stuff. There's a lot of situations you can expand this to, of course, but it is nice to see these questions that actually have a real world context to them. Those first two questions were the toughest one on here. Realize that on your chapter test, there is going to be at least one question like this, and it'll be pretty similar to one of these here. So just make sure that you understand how to go about doing these questions. Anyway, question 3, this is more back to more classic kind of stuff that we started this unit with. This I'm going to fly through even quicker, but make sure you're making your corrections as you go as we need. When you have just a standard question where you're multiplying or dividing or even adding or subtracting, always, always, always start by factoring the whole thing. So I'm going to factor the first piece up here. That's a sum product rule question. Sum of -3, product of -10, that would be -5 and +2. So this makes it x minus 5 times x plus 2 over x squared minus 36. Remember that's something square rootable minus something square rootable. That's a difference of squares. Hopefully at this point we know how to identify this. We've been through this quite a few times. Difference of squares comes when you have something minus something and you can square root each piece. To take care of a difference of squares, this makes it x minus 6 times x plus 6, right? So you just square root each piece. X minus 6, that's the square root of this, minus the square root of this, times the same thing with a plus sign. Times this one on top. Well, this doesn't look like a normal sum product rule question. We don't have like 3 pieces to it. It also doesn't look like a difference of squares because there's no subtraction. That leaves us only one choice. We got to see if we can pull out a greatest common factor. Think about any number you can divide both of these by. Well, the number that I can see right away is I can pull a 12 out of both of those things. So if I pull a 12 out, I got 12 on the outside. And if I divide each of these things by 12, I'm left with x plus 72 divided by 12 is 6. Over x plus 5, good news on that one, that is already factored. We can't go any further than that. So x plus 5, that's going to be that piece. Once you have everything factored, notice how they're all in their own little sets of brackets. When you're multiplying fractions together, you can just draw the line straight across. From here, you can cancel out anything that is the same. There isn't a lot that's the same. We were close with the x plus 5, and we had an x minus 5 over there. Darn, I wish that was kind of the other way around, but it is what it is. The only thing I can see canceling right now is x plus 6, and that is actually about it. So what we're left with is the final answer. I'll take this 12, I'll put it out in front just because maybe it'll look better out there. I've got 12 times x minus 5 times x plus 2 over x minus 6 times x plus 5. And as sad as it is, that is as low as that goes. We can't go any further with that at all. Moral of the story is here, when you multiply rational expressions together, sometimes it's nice. Sometimes you get a million things that cancel out. Other times, like this one, you don't really get a lot. We only had one thing that canceled out. That's better than nothing, but we only had one thing, right? Anyway, for NPVs now, non-permissible values, look at your denominator when it's in fully factored form, list out wherever x would be equal to 0. If we look at this one, x would be equal to 0 if x was 6. So I'm going to say x can't equal 6. If I looked at this one, x would be equal to 0 if it was -6. So I'll say x can't equal -6. And then as for this last one, x would be equal to 0 if it was -5. So x cannot equal -5. Anyway, moving on, 2 more questions here. Subtract and simplify, list your NPVs. When you subtract, it's kind of like multiplying and dividing in that you have to start by factoring. But after that, then things go totally different, right? If we're going to start by factoring this, first of all, we have nothing to factor up here. So I'm just going to leave it as 5 over. This is a pretty classic difference of squares. That's going to be x minus 7 times x plus 7 minus 2. Once again, we can't really do anything there. So it's just 2 over. And this one's a pretty classic looking sum product rule, right? So 2 numbers with a sum of -9, but a product of +14. So that would be x minus 7, so -7, and x minus 2. Now, to subtract fractions together, they have to have a common denominator. These denominators are not exactly the same. Notice this one on the left does not have an x minus 2, and this one on the right does not have an x plus 7. We can fix that, of course, just by tacking that on to each fraction, right? Whatever you do to the top of a fraction, you got to do to the bottom to keep things the same. So if this guy needs an x minus 2, I'll put an x minus 2 up here and an x minus 2 down there. As for this guy, it needs an x plus 7, so I'll put x plus 7 up here and an x plus 7 down there. Now, what this is going to do is it's going to make it so we can actually subtract our numerators. Before I do that, though, I often like double dipping this through just so I can have this all expanded out so I can combine my like terms. If I double dip this through, 5 times x is 5x, minus 5 times 2 is 10. And then that's, all, of course, all over x minus 7, x plus 7, and x minus 2. Minus, if I double dip this through, I'm left with 2x plus 2 times 7 is 14. All of that, again, over x minus 7, x minus 2, and x plus 7. Don't worry that your factors are in a different order. Remember, with multiplication, order does not matter. We're only one step away from being done here. We got to combine our like terms, but be careful. I chose a subtraction question on purpose. When you subtract, you got to think of this whole thing minus this whole thing here. So think of it this way. What's 5x minus 2x? We want to deal with our like terms, so I'm dealing with the x's. 5x minus 2x, well, that would be 3x. And then the tricky piece here, negative 10 minus positive 14. Don't forget about the minus there. It's not that we're just adding 14 here. We're subtracting the 14. So negative 10 minus 14, that's actually negative 24. So this is 3x minus 24 all over x minus 7, x plus 7, and x minus 2. That right there would work as a final answer. You could go a little further. You could factor a 3 out of the top, but it's not going to get you anywhere. So I'm not going to bother doing it. You'd have 3 times x minus 8. X minus 8 wouldn't cancel out anyway, so you didn't gain anything from that. Anyway, NPVs, of course, on this one. Look at your denominator, find out what would make them equal to 0. I'll just use the denominators right here. X can't equal 7, because that would make this piece equal to 0. X also can't equal negative 7, because that would make this piece equal to 0. And then lastly, x cannot equal positive 2, because that would make this piece equal to 0. All right, we got one last question to go through here. Solve the following rational equation. Okay, so it's an equation again, kind of like what we saw in those word problems, except the nice thing here is this one's already set up. It also wants us, of course, to list our NPVs. I didn't list my NPVs in those first 2 questions today. Oftentimes, because when you have a word problem, usually your NPVs, they don't really matter as much. You can always list them, though. It's always a good habit to get into, but it is what it is. Anyway, so first of all, this thing, first things first, you always want to factor everything. I don't see anything we can factor here. There's nothing I can pull out of any of these. So I'm just going to leave it as is. Notice if we treat these already as pre-factored little chunks like this, we can think of this left fraction as needing an x plus 7. So I'll give it an x plus 7 on the top and the bottom. We need this middle one here to have an x minus 2 on the top and the bottom. And we need this last one here to have an x plus 7 on the top and the bottom so that they all match. Now I got a little lazy here. I guess, I'll go like this. So x plus 7, x minus 2, and x plus 7 here. So yeah, x plus 7 there. So that way they all have the same denominator as well. Once they all have the same denominator, we can be really lazy and we can just ignore it altogether. What this is going to leave me with is 3 times x plus 7 plus 5 times x minus 2 equals 2 times x plus 7. Now to solve this, I just need to double dip everything through. So if I double dip this through, I'm going to be left with 3x plus 3 times 7 is 21, plus 5 times x is 5x, 5 times minus 2 is negative 10. And then this equals 2 times x, which is 2x, and 2 times 2 times 7, which is 14. There you are. My mouth is moving faster than my brain, it seems. Anyway, now we want to combine our like terms. I'll clean up the left side first. 3x plus 5x is 8x. 21 minus 10 is plus 11. That equals 2x plus 14. Now let's gather all of our x's to one side. So I'll minus 2x from both sides. So if I take away 2x from here, I got to take away 2x from here as well. So this gives me 6x plus 11 equals 14. Might as well move the 11 over to the other side now. So minus 11 from both sides. This is going to give me 6x equals 3. And then one final step, just divide by 6 on both sides. And we have x equals 0.5, or if you prefer 3 over 6 or 1 over 2, however you want to say it, right? So x is 0.5. That's all well and good. And last but not least, list our NPVs. This was already factored for us. So just look at where each piece was equal to 0. X cannot equal positive 2. And for the x plus 7, x cannot equal -7. That's it. We're all done, right? Anyway, hopefully that was sort of helpful at least. For practice, you need to complete any previously assigned practice questions. See the ones in your note package at the bottom of each lesson. Make sure you're checking your answers on these ones. Like not only just completing them and saying, oh yeah, I did them. Check the answers at the back of the book. Make sure you're doing them correctly. And if you need help, make sure you are reaching out, whether it's to one of your peers or whether it's to me as your teacher. Anyway, if you need any extra help, please let me know.